Welcome everyone to lecture 26 for MAT353. This is a lecture intended to be viewed on Wednesday, April the 8th. So we are going to continue today with our discussion of cylindrical coordinates. We mentioned last time that cylindrical can be characterized as polar plus z. So the xy plane, the horizontal plane, is being represented in polar coordinates here, r and theta, and we leave the z-axis in its Cartesian form. So the variables are going to be r, theta, and z, and our dv expression is going to look something like this. We're actually going to rearrange the order of the dr, d theta, dz shortly, but this is the idea for, in general, you've got the extra r term from the expression of the xy plane and polar, and you've got your z variable as well that remains in its Cartesian nature. And we had some equations that allowed us to convert back and forth between rectangular and cylindrical. Namely, these two equations for x and y, and these are identical to the equations that we had for polar when we were thinking about double integrals, and z is just z. Also, a holdover from polar, or something that carries over due to the polar nature of the horizontal plane here, is the expression r squared equal to x squared plus y squared, which can easily be seen from these expressions of x and y. If you square both of these and add them up, factor off the r squared, and cosine squared plus sine squared is 1. So this is actually a bit redundant. This information is carried in these two equations as well, but it's useful to bear this in mind. If you're working with triple integrals and you start to see x squared plus y squared expressions in your integrand, that is a hint that polar, or rather cylindrical, might simplify the form of the integrand. So the next goal is to get some intuitive sense of what types of regions will be easily represented in cylindrical coordinates, and to that end we are going to consider both what rectangular boxes look like in cylindrical and also what our grid surfaces look like in cylindrical coordinates. So rectangular boxes in cylindrical. Rectangular boxes, first in Cartesian, to remind ourselves, look like regions of 3 space of this form. So in particular, the analytic characterization of a rectangular box in Cartesian coordinates is that the x, y, and z variables all have constant bounds. And if I impose such bounds on these variables in Cartesian, we end up with a region that looks like what you might expect given the description rectangular box. I had written this as like b minus a, that's the length of the interval where x is allowed to live, and that's true, but it's better to rewrite it here as delta x. We've got a change in the x direction, we've got some amount of change that's allowable in the y direction, again that would be d minus c if you wanted to give it numerically, and we have a change in the z direction, f minus e here. And our dv expression in Cartesian ends up looking like dx, dy, dz. In cylindrical, a rectangular box, the analytic expression of a rectangular box, we're going to proceed by analogy, and we're going to impose constant bounds on the 3 variables that make up a cylindrical coordinate system. So r is going between a and b, theta is going between alpha and beta, and z is going between e and f. Here we're obeying the convention that angles get Greek lowercase letters, and we're keeping the same e and f from Cartesian, from our expression of rectangular boxes in Cartesian, just to emphasize the fact that z plays the same role. It's essentially the same z that it was before from Cartesian. If you just take these constant bounds for r and theta, you're getting what we would call a polar rectangle. We're getting a rectangular region in polar coordinates, and you can see that here is the base of this volume that we've drawn. So here's r equal to some constant. This next curvy line out here is r equal to some larger constant. And having swept through this turn is theta moving from a small constant value to a larger constant value. So this depth here, or width if you prefer, is r delta theta as it was in polar. If we moved further out from the origin, we would see it swinging through a larger arc for the same change in the angle. Again, that's like how the tip of the baseball bat moves through a larger arc than the portion of the baseball bat near your hands when you swing the bat. So the actual arc that is moved through depends on how far from the origin you are, which is why we have an expression of the form r delta theta. The change in the radius here is just delta r, and the change in z is our delta z. We're taking this polar rectangle and we are translating it through some vertical shift, delta z, and that gives us a volume, a three-dimensional volume of this region. And again here our delta v term is going to be the product of these three changes. And so we will pick up an extra factor of r, and we will also have our delta z, delta r, and delta theta expressions. So this is what a rectangular box looks like. There are more versions of this. You can make them look slightly different. If I let alpha and beta be 0 and 2 pi, for instance, I can have full circular symmetry in such a rectangular box in cylindrical coordinates. If I let little a be 0, I can pull this all the way back to the origin, and I would have sort of a wedge-shaped slice here that we were looking at. But this is one version of what rectangular boxes look like geometrically. Analytically, it's always about letting each of the three variables be bounded by constants, just as it was in Cartesian coordinates. Let's think about grid surfaces. So when we thought about coordinate systems for the plane, we considered grid curves or grid lines where we set each of the variables equal to a constant. We're going to do the same thing here for triple integrals, for coordinate systems, not integrals yet, rather, but coordinate systems that represent three space. We're going to go through and we're going to set each of the variables equal to a constant, and we're going to think about what types of surfaces those equations represent. And that will give us some sense of the way that the different coordinate systems divvy up three space, and thereby give us some sense of what types of regions will be naturally expressed in the different coordinate systems. So in Cartesian, if we set x equal to a constant, we get a vertical plane parallel to the YZ plane. We've thought about these before when we were working with three space generally, but something like x equal to 1 could be the plane that I have sketched here. You go out along the x-axis a distance of 1, no constraints have been placed on the y or the z axes, or y or z variables, and so those are allowed to take all values, and you get a plane which is parallel to the YZ plane, but moved out along the x-axis some distance. Likewise, if we set y equal to a constant, we get a vertical plane which is parallel to the xz plane, and if we set z equal to a constant, we get a horizontal plane parallel to the xy plane. Z could be set to be 1, for instance, and with no constraint on x or y, we take all xy pairs together with z equal to 1, and we get the horizontal plane parallel to the xy plane, but moved up a distance of 1. So these are what our grid surfaces look like in Cartesian, and this means that the Cartesian coordinate system divvies up three space into these rectilinear type of box regions. It's the way that it views three space, and any region that sort of fits along surfaces of this type in a natural way will be well represented in Cartesian coordinates. Cylindrical, on the other hand, we can set the three variables in cylindrical equal to constants, and we see grid surfaces of this type, or of these types. So if we take r equal to a constant, we're going to get cylinders having the x-axis as their center line, extending infinitely up and down. So r equal to 1, for instance, in polar coordinates, that just gives you the unit circle centered at the origin. In cylindrical coordinates, we're getting that unit circle centered on the z-axis, but with any positive or negative z value allowable. So what we're seeing here is the unit circle centered at the origin from polar, shifted or translated through all positive and negative z values. So the same unit circle, but with any constant value for z, and that gives us the whole of this cylinder centered on the z-axis and extending in both the positive and the negative z directions. Hopefully that makes sense. If I took z equal to 2, if I took r equal to 2, I would get a larger concentric cylinder that contains this one. It's got a larger radius and still extends in both directions. Feel free to ask me questions about any of this. We definitely want to develop the intuition for these coordinate systems. That's important. This is how you know when to apply different techniques. Like, I can just hand you a region and ask you to integrate over it, and you need to have some sense of which coordinate system is going to be best for representing this region, and developing an intuition for the types of regions that can be easily expressed in the different coordinate systems is key to that sort of meta-analysis for a math problem. Like, here's the problem, which techniques do you want to use? You have to have a good sense of which regions will be easily represented in the different coordinate systems to know how best to approach the problem. So, moving on, let's take theta equal to a constant. This is going to give us a half plane with z-axis, with the z-axis as its boundary. I redrew this picture several times. I had to redo this slide several times. I'm still not as happy as I could be. The idea is take the xz plane, first of all, and just take the half of the xz plane where x is positive. So the xz plane extends in positive and negative x direction. Just take the half of the xz plane where x is positive and swing that like a door around through some angle theta. And the door is hinged on the z-axis here. So it's fixed on the z-axis, that remains fixed, but the rest of that plane swings around through some angle theta. And because it's not terrible, this is definitely the best version I came up with of this picture, but I will recommend that you also take a look at figure 3 on page 1085 of your book if you are having some difficulty interpreting the picture that I've drawn. Page 1085 is dealing with theta equal to a constant for the spherical coordinate system, which is the next coordinate system we'll discuss, but it has the same geometric representation. So even though the picture for theta equal to a constant there is technically for spherical, it's the same picture that we would draw in the cylindrical case. Stewart doesn't draw it for cylindrical for some reason, so we'll make use of another picture that's equivalent. And then when we set z equal to a constant, we again get a plane, a horizontal plane, which is parallel to the what we will now call r theta plane, since that horizontal plane z equal to 0 is represented in terms of r and theta now. But if you set z equal to any constant, you get a horizontal plane parallel to the r theta plane at the appropriate height above or below the r theta plane. And it's been drawn a little bit lopsided here, but it's the same picture that it was for Cartesian. Z equal to a constant is the same kind of level, or the same kind of grid surface here as it was for Cartesian. So hopefully that helps you out here. We've got theta swinging around like a door. You've got different cylinders you can represent by setting r equal to a constant. And you've got horizontal planes that can also be achieved by setting z equal to a constant. So if you imagine all of these surfaces together, we would have a bunch of concentric cylinders. We would have a bunch of these half planes sticking out from them in a radial way. And we would have a bunch of horizontal planes bisecting that whole expression. And those are the grid surfaces associated with cylindrical coordinate systems. So hopefully that gives you some sense of what types of regions can be easily represented in cylindrical. And not surprising, it's regions that have somewhat of a cylindrical nature. So when your region has some kind of tube-like nature, then it is generally a good bet to try to represent it in cylindrical coordinates. And we're of course going to do examples and sample problems so that you can get some hands-on experience with this stuff. The ultimate point of having a new coordinate system, at least in the context of this class, is to be able to simplify certain integrals by representing them in the new coordinate system. So we do need to think about what do integrals look like in cylindrical coordinates. So if we have a continuous function of x, y, and z, and it's continuous on a region R, and R is given in this form, and we're actually not going to require R to be a rectangular box in cylindrical coordinates. We're going to let r and theta be bounded by constants, but we're going to allow z to be bounded by two functions of r and theta. So we will have a polar rectangle here in the r theta plane, but then our bounds on z could perhaps vary across. So you can imagine taking a cylinder and maybe slicing the top of it at an angle, like an old column that's been broken at an angle. And then you could even have something like a rounded bottom to the thing if you wanted to. So our z bounds are going to change potentially depending on where in the r theta plane you're considering, but r and theta will both have constant bounds. And again, we'll do plenty of examples to get a better sense of what I'm saying here. If you have a function of three variables that is continuous over such a region, then the triple integral of that function over that region can be expressed in this form. So this is going to be an r dz dr d theta integral. This is all my dv expression here. And we're doing the z variable first, because it's the z variable that has limits of integrations which depend on r and theta. So just as we saw when we were considering double integrals over more general regions, over type 1 and type 2 regions, your innermost integrals can be variable, but your outer integral at a minimum has to have constant limits of integration. Here it's both of the outer two integrals, the middle integral and the outermost, both have constant limits of integration. But my innermost integral is allowed to have limits of integration that depend on those variables. When I take an antiderivative and I plug in these limits of integration, I'll be introducing more r and theta expressions into my integrand, but then those variables will still be integrated out through later integrals, allowing me to ultimately arrive at a numerical answer for the problem. So, inner integrals in general are allowed to depend on variables, but outer integrals have to be constant, and in particular your outermost integrals need to be taken with respect to those variables which your inner integral depends upon. So the limits of integration of my inner integral depend on r and theta, and an integral with respect to r and an integral with respect to theta are still to be taken. So I will integrate out any extra r theta terms that get introduced when I plug in these limits to an antiderivative. So that's the idea, and here x has been rewritten as r cosine theta, y has been rewritten as r sine theta, z is still z, it maintains its identity as you move from Cartesian to cylindrical, and our dv expression is going to be r dz dr d theta here. So again, to note explicitly, we are dealing with a polar rectangle in the r theta plane. R is bounded between two constants, and theta is bounded between two constants. But this region, big R, is not a rectangular box in cylindrical because z is not bounded between two constants. The bounds on z are allowed to depend on both r and theta. And the next note that we want to make is our dv expression being r dz dr d theta. You could think of it as dz and then your r dr d theta from polar, and we just rearrange that expression to introduce the r factor into the integrand. As we mentioned, this polar plus z typification of cylindrical is the most common, but there is no problem representing cylindrical coordinates as polar plus y or polar plus x. In those two cases, you would have your r equal to a constant grid surfaces look like cylinders, in this case for polar plus y, which had the central axis equal to the y-axis, and here your r equal to a constant would give you cylinders whose central axis was equal to the x-axis. In those two cases, your dv expressions will not involve a dz, but will rather involve a dy and a dx respectively. Here, polar plus y, it's the xz plane that's being represented as r and theta, and your y-axis remains your y-axis. Here for polar plus x, it's the yz plane that's being represented in terms of r and theta, and your x-axis remains as it is. The last point that we want to make, our next step here is to actually start computing some integrals, to have some problems thrown at us, and to realize that we should compute them in cylindrical coordinates. We're going to do that for the next part of this lecture. But the last little point that I want to make is that it's actually also relatively easy to represent cones in cylindrical coordinates. So if I take the upper half of this cone here, this is going to be the cone whose edges are on the 45, I can represent that with just z equal to r. So for any value of r equal to a constant, your z value is also equal to a constant, and we're getting that circle r equal to a constant represents translated up through the z value. So like when r is 1, so that you're in the r theta plane on the unit circle centered at the origin, your z value is also 1, so we take that unit circle and shift it up a distance 1, and so forth. As you move up, the circle widens, or equivalently, as you move out to wider circles, your translation through along the z-axis is a greater distance, is done over a greater distance. So for larger circles, circles of larger radius, you translate up further along the z-axis, and that's where the circle meets this surface. So z equal to r give us the upper half. These equations give us the upper half cones, and I could take z equal to 5r and get a sharper cone, or z equal to 1/2 r and get a broader cone as well. If I take z equal to negative r, I'm getting the lower half of the cone. R, if you remember in polar, is always non-negative, and so if I want to see the lower half of the cone, I have to slap a negative sign onto r to make my z values negative so that we're below the r theta plane there. Stewart doesn't get this quite right. In section 15.7, which we're covering now, Stewart just says r equal to theta is the full cone that we see here in our third picture, and I fully disagree. That doesn't make sense if we're taking r to be greater than or equal to 0. Perhaps Stewart is allowing for negative values of r, which I find unsatisfying. So we're taking r to be greater than or equal to 0, and so we have the upper cone as z equal to r, the lower cone, lower half of the cone is z equal to negative r, and to get the full cone, which extends in both directions, we take z squared equal to r squared. Note that this would give me z equal to plus or minus r if I were to take the square root of both, which would be another fine way to represent the full cone. Notice that things that we usually call cones, like traffic cones and ice cream cones, are actually half cones by this mathematical definition. A full cone extends in both directions, which is not usually the way that we talk about the word cone, or conceive of the word cone in our colloquial use of that word. Alright, that'll wrap up the basics. So the next thing that we're going to do is a bunch of examples and a bunch of sample problems. We'll spend the rest of today's lecture looking at some applications of cylindrical coordinates and integrals in cylindrical coordinates. Thank you, folks.